Hello everyone. This video is intended to help you with rotational dynamics problem solving and the strategy that we use. I've put a reasonably difficult problem here, but nothing too crazy. All right, so we have three pulleys that are joined together on an axle. We're given their masses and their radii, and three equal forces are applied to each pulley, and it says here that the counterclockwise is on the largest and smallest pulleys, and the clockwise is to that middle one in the middle. So what I'm going to do is I'm just going to draw my FBD, because you know what? That's what we do when we do dynamics problems. We draw FBDs. Did you know that? I knew that. So I'm just going to, it doesn't matter where we draw it. I'm just going to, to make life easy, I'm going to draw it here. Here's one of the forces, 3mg. And this will make it rotate counterclockwise as well, 3mg. And the other one goes the other way, trying to make it rotate clockwise, 3mg. Now, technically, those arrows should be the same length, but, you know, I'm not perfect. And apparently, neither is writing 3mg. 3 m. Seriously, do you see that? Why does that keep happening? 3mg. The m just weirds out. Anyway, okay. After that, you've drawn an FBD, and as you know from our previous topic, when we used to draw FBDs, we would do the sum of the forces equals MA. But now we have to do the sum of the torques equals I alpha. So sum of the torques equals I alpha. Here's the thing. We have three pulleys that are fused together, each with their own moment of inertia. So it's kind of like forces that are pushing perhaps three masses that will accelerate as one, like F equals MA. In that case, we would add the masses together. Here, we are going to add their moments of inertia together to get the total moment of inertia. A pulley, a solid pulley, is considered a disc or a thin a cylinder, and the moment of inertia for a cylinder or solid disc or pulley is 1/2 mr squared. So to get I total, we need to add them all up. Here we go. So I total is going to equal 1/2 mr squared, the larger pulley, plus 1/2 smaller pulley, mr squared, plus the smallest pulley, 1/2 mr squared. And because I'm a genius and I can do this stuff in my head, you're going to get that the total moment of inertia is 18 mr squared. Now we can go back and start doing some solving kind of stuff. So here we go. I'm going to start with the sum of the torques equals I alpha, meaning I'll add up all the torques that cause this mass to rotate. And here we go. We've got 3mg technically in the positive direction, but as we've spoken about in class, whichever way it's rotating is positive. Yeah, you should know that technically counterclockwise is going to be positive and clockwise would be negative. But remember, it's okay to say whichever way it's moving is the positive direction. So back to this, we have 3mg acting at a distance of 3r. We've got 3mg acting at a distance r. And we've got 3mg trying to make it rotate clockwise at a distance 2r. And that will make the total mass slash moment of inertia, however you want to think about it, have an angular acceleration. And when you do all this, there's a couple things here that we can do to make life easier. We can get rid of the m. There is an m in every term. We can get rid of one of the r's, r, one of the r's. And I believe that this will reduce down eventually to, excuse me, 6g equals 18r alpha. And from here, we can get that alpha is simply g over 3r. Algebraic makes it so much easier, doesn't it? And then after that, are we solving for anything? I think so. We're supposed to solve for the angular displacement of the pulley during that time. Okay, no biggie. You've done this before. You are professionals. So what we're going to do is I'm going to list some variables here. I've got omega I which is 0. Omega final, we don't know. Alpha, hey, we just got that. That's G over 3R. Delta theta, I believe that's what we're looking for, and delta T is simply T. So the expression we're going to be using is the delta theta expression equals initial velocity times time, which is 0, plus 1/2 acceleration times time squared. So we have delta theta equals 1/2 G over 3R times T squared, or delta theta equals GT squared over 6R. And that's it. All right, let's sum this up really quick so that I don't bore you too much. Although the sound of my voice, I hear, puts people to sleep and is soothing for a bedtime story. All right, we don't know what we're talking about at this point. Here's some highlights, though. When you're doing these rotational equilibrium problems, you want to draw a free body diagram of the object. Just like we did in the past when we drew free body diagrams on dots, this is more about the object so we can see where the torques are applied. If there are multiple objects rotating together, you will add their moments of inertia. That's why this problem was chosen. And after that, you do the sum of the torques equals I alpha, just like we used to do in the past. F equals ma. Now it's torque equals I alpha. For our purposes, whichever way it's rotating is the positive direction. Please always, always, always do that. It'll make your life easier. The AP scoring guide expects you to do that. It's all good. In the back of your mind, you should know that counterclockwise is officially considered positive and clockwise is considered negative. And then you might have to do some kinematics. Okay, we just did that. List your variables, do what you know how to do. It is possible that at some point you may have to use our friends Rho-mega and Ralpha and Rho-theta or Wrangle, depending on your preference, to go from angular quantities to translational or tangential quantities. But other than that, I hope this video has basically summed up what we do when it comes to rotational dynamics problems. And I thought I did a good job. I did probably 3 out of 5 stars, and I wouldn't change a thing.